Hello everyone, my name is Wang, and I am a PhD student in University of Technology of Taiwan. The subject of my presentation is optimization of thermomechanical parameters for growing oxide and on metal system. Here is the plan. First, I will introduce some context, and then is the thermomechanical modeling for nickel chrome and chromium system. The third part is the method for processing the experimental results, and then is the results of coefficient optimization and activation energies. Finally, I will give some conclusions and perspectives and prospects. For application at high temperature, chromium-based alloys have been developed in order to form chromium. We can see that before the oxidation, the sample surface is polished as a mirror, Risca 2 micrometer. And the sample after oxidation, we can see that there is a chromium layer, chromium films at the surface of the sample. The chromium film provides a good protection against the further oxidation. During the oxidation and due to the addition between the oxide film and the substrate, the stress arises on both sides of metal and oxide interface. There are elastic stresses, viscoplastic stresses, thermal stresses in both the oxide film and the substrate. And there is particularly growth stresses in oxide film. The problem is that there are several parameters to be identified with these stresses. To obtain the numerical solutions, we use MATLAB and applying the classic Honga-Kuta method. The different screen rates have been taken into account. There is elastic part, viscoplastic part, thermomechanical part, and growth ring part for oxide. For the growth ring part, the H-ox is the thickness of the oxide layer, which is evolved with time. For the viscoplastic strain, a northern half-power law is used. And with the expression of G-ox, we can see that G-ox is related to the oxide grain size and the activation energy, Q, which is this expression. And the total strain rate of metal is the elastic strain rate plus viscoplastic strain rate plus thermal strain rate. And the total strain rate for oxide is elastic strain rate plus viscoplastic strain rate plus thermal strain rate plus growth strain rate. An isothermal condition is considered. All the material parameters related to temperature are constant. So we also have the continuity condition at the metal-oxide interface, which gives us the total strain rate of metal and the total strain rate of oxide is identical. And the force of balance equation gives us the stress in metal multiply the thickness of metal plus the stress in oxide multiply the thickness of our oxide equals to 0. And the factor 2 means that the oxide grows on top surface and bottom surface of the substrate. From the previous equations and to adapt it to numerical solution, we can get equation, and we can get this equation. There are 11 material parameters to be identified. However, some of them can be determined by other measurements. So here we will focus on G-ox and D-ox. G-ox is the viscoplastic parameters, and D-ox is the growth ring parameters. This Cauchy problem can be extracted like this equation, where the stress is an unknown function of time t, and the stress rate of oxide is a function of t and the stress itself. At the initial time t0, the stress has a value sigma 0, and the function f, t0 and sigma 0 are known. So the classic Honga-Kuta method is applied. By choosing the time step delta t, we can see that the tendency of the simulation are very close. The alloy contains a mass of percentage of 28% of chrome, symbolized by nickel 28 chrome. The chemical composition of nickel 28 chrome is given in table 2. The thermal loading is shown in figure 6, and the loading is like oxidation at the 1000 degree at 3 hours, followed by oxidation at 900 degree for 3 hours, and then 800 degree for 3 hours. Bragg's law and the law of sine squared C can help us to determine the stress. The Bragg's law gives us a relationship between interplane distance d HKL and the diffraction position of a given peak, theta. With the Hooke's law, we can finally get the law of sine squared C, a function of stress. By drawing the ln, 1 divided sine theta as a function of sine squared C, we can see that the stress is in the slope. In fact, the experimental results we obtained is the images of diffracted rings. Each ring presents a peak of oxide or a peak of metal. We divided these rings in several gamma. By integrating each gamma, we can obtain the intensity on function of 2 theta. For fitting the peak, we also tried several methods and choose the best method. We can finally get this figure. It is intensity on function of 2 theta for all the peak and for all the gamma. For one peak, we can also draw the figure 2 theta on function of gamma, and finally we can draw the curve of sine squared C. We can see that this relationship between ln 1 divided sine theta on function of sine squared C is linear, so the stress is determined. The time-dependent stress can be obtained by for temperature plateaus at 800 degree and 900 degree and 1000 degree by applying the method sine squared C stresses. We have a hypothesis here. At 800 degree and 900 degree, the growth stress for parameters for oxide dox is equals to 0. So that we can start to optimize with the viscoplastic parameters for oxide, Gox, at 800 degree and 900 degree. Here is the example for fitting for parameter Gox at 900 degree and 800 degree. With the values of Gox at 800 degree and 900 degree, we can obtain the theoretical Gox at 1000 degree. And using the theoretical value of Gox at 1000 degree, we can optimize the Dox and Gox at 1000 degree at the same time. For the sample, we have several groups. The basic sample is nickel 28 chrome. And the first group is import reactive element yttria. The layer was introduced using different exposure times in a PVD chamber to vary the quantity of yttria in the alloy. The exposure time we have 10 seconds, 50 seconds, and 100 seconds. The second group is doping reactive element zirconium. In this work, for the metallic substrates that have been subject to the ionic implantation of chromium, 3 doses have been applied. 15 powers of 10, 15 powers of 10 multiplied 5, and 16 powers of 10 ions per centimeter square. Here is the result. For the growth parameter diox, we can see that the diox is decreased with the exposure time increase. And for the geox and the activation energy, we can see that the activation energy increase with a longer exposure time. For the second group, doping the reactive element zirconium, the diox also decreased versus the fluence. And for the redox and the activation energy, we can also get the same conclusion that the activation energy increased with the higher fluence. So here is some conclusions. We found the best simulations of peak profiles. For each sample, over 13,000 images were processed to obtain the time-dependent stress, and 7 samples were treated. With MATLAB and the classic Hongo-Kuta method, it is possible to identify unknown parameters. In this instance, the viscoplastic parameters for oxide and the growth stress parameters for oxide have been identified. For the raw material, the yttria-coated material and the zirconium-coated material, the creep parameters geox decrease with a lower temperature as a proof of thermal activation of creep mechanism following a Arrhenius model. For this nickel 28 chrome and chromium and yttria coated or zirconium doped and chromium system, when the reactive element increase, the slope of Arrhenius curve becomes higher, with corresponding to the increase of the activation energy. And thirdly, by the increasing the quantity of yttria-coated or zirconium-doped, the growth string parameter diox decrease. The diox parameter may be related to the ratio of cationic and anionic flow occurring with the green boundaries as the oxide layer grows. That's all. Thank you.